Hello, we are SGS Group 3. My name is Zyle.
And I'm Lot. Today we will present our network topology for assignment 3, and here are our ID cards.
So in task 1, we created our design. Our topology demonstrates a school environment with outsourced IT management. So we used 4 subnets, which you can see in this table, and each of these subnets is using a Class C private address, which is shown in Figure 1. Now let's swap over to Cisco Packet Tracer. And as you can see here, we have a top-down hierarchical structure. We've got our layer 3 devices as the router here and the switch just below. So the role of the router in this configuration is to allow all of the subnets to communicate with one another. This is also known as inter-subnet connectivity. And as you can see, each subnet is also ordered into different color blocks, and each subnet is also connected by a switch. So this topology is known as a star-bus hybrid network topology, and you'll also see that each PC is configured with its IP address, which links to the default gateway, and all of these addresses fit within our subnet. So in order for us to verify that the end-to-end connectivity is working throughout the entire network, we need to come up with a few sample pings. So in the slides here, we've prepared a few types of pings. We're going to have intra-subnet through Xyle PC1 and PC3, and we're also going to have inter-subnet pings throughout the entire network, and we'll finish off with lock PC9 in subnet IT, attempting to ping an invalid IP address that's not within the network. So as you can see, we have our expected results on the second to last column on the right side, and we are going to fill this table. All right, so let's transition back to Cisco Packet Tracer, and we're going to start with Xyle PC1 to PC3, successful. Now PC2 to PC5, successful. Now PC7 to lock PC2, successful. Lock PC10 to Xyle PC4, successful. Now lock PC3 to Xyle PC1. And now we click on lock PC9. This is going to navigate us to the command prompt, and let's run ping to the invalid address. And we can see that the destination host is unreachable, which means that the ping has failed. So navigating back to our slides, we can see that the actual results match the expected results, and the result has been updated to prove that the hypothesis is correct. So in task 2, the focus was on configuring two VLANs within the same subnet. So table 3 shows the configuration for each VLAN, and we can see that here, for each VLAN, it's using the /29 address. And since we have two of those, we can combine them to make a wider /28 address. It's important to note that each VLAN uses a subnet address that's within the /28 domain. So that's why we classify the subnet students as the same subnet. So we'll also see that our hosts, that is our devices, are configured with IP addresses 1.2 and 1.3, and they're assigned to VLAN 10. And we can see within the switches configuration that the ports 02 and 04 are assigned to VLAN 10, which matches the result in table 4. One important thing to note is that the first usable host addresses for each VLAN is going to be used for the sub interface in the router, and we'll talk about that next. However, the main concept that we wanted to articulate in task 2 is to answer the question of what is the significance of layer 2 and layer 3 in VLANs. Now let's see how layer 3 is used to conduct inter-VLAN communication. So in theory, from PC2 to PC3, the packet should travel to the switch, over to our router, back to the switch, and back to PC3. The reason why we have to use the router, which is a layer 3 device, is because it is hosted in a different network or subnet seen here. So even though they all fit within the student subnet, it's still going to have to access layer 3 because there's no gateway for this subnet. The gateway in this case is configured as a sub interface using these addresses. So let's go ahead. We go to the switch, and then we'll also see it's using the layer 2 information, and now it navigates to the router. So the reason why data is able to flow from the switch to the router is through the trunk configuration. The trunk is going to allow data from VLANs 10 and 20, not exclusive to one of them, to flow over this link. So as we can see, it goes to the router, back to the switch, and then over to the destination. And vice versa. And as you can see, it's successful. So how about the configuration to other subnets? Well, we can try PC1 to PC5, that's also successful. PC2 to PC7, successful. PC3 to PC2, lock PC2, and that also works. So as you can see, the trunk and sub interfaces allow for total connectivity across the network.
Now we will make a demonstration on task tree. This test aims to show how layer 2 and layer 3 addresses behave in communication, and our approach is to delete the ARB table to simulate flash communication, utilize simulation mode and video information to inspect how packets traverse, so that we can be able to capture and analyze addresses changes as ingress and egress. And we will bring from 0BC1 in student subnet to log BC5 in IT subnet, and this is the expected outcome. Now we will make a live demonstration on task tree. So no ARB entry found. So now we try to bring from log 0BC1 from student subnet to log BC5 in IT subnet. So you can see there are two messages because the destination is outside subnet. BC01 needs to send an ARP request to learn the MAC address of this router before forwarding the packet. So after receiving the ARP reply, 0BC1 send a request to log BC5. So now let's take a look at Xio router where both ingress and egress happen. So at ingress, the router receives a frame from BC1 at layer 2. It checks for a matching MAC address and accept the frame, and then the original Ethernet header is stripped off because the layer 2 is only used for local delivery. So you can see the Ethernet layers, layer 2 is different. And at layer 3, a router with IP header, the source IP is 192.168.1.2 and the destination IP is 192.168.1.34. Next, at egress, the router prepares a new Ethernet frame. The source mask is Xio router and the destination MAC address is set to the next hop router, which is log router. So to summarize, layer 2 address change and layer 3 remain unchanged at ingress and egress. So when a packet bridge log router, the same process happens at ingress and egress. So after the ICM request reaches log BC5, it sends back an ICMP reply to confirm that the destination device is reachable and responding. And this return journey follows the same routing process, just in reverse. And at the end, you can see the status is successful. And this is also the end of the task 3 demonstration. So now let's move on to task 4. This is our web server setup for task 4. We assign a static IP of 192.168.1.42 with a flash 29 subnet, enable HTTP and HTTPS services, and connected it to a switch C with all the hosts, as shown in the figures. And our hypothesis was that all hosts should be able to communicate with the web server, as shown in the two tables. Each host sent a request to the server, and the expected result was a success. And now we will try to fill out the actual result in Packet Tracer. Now we try to bring from all the hosts to the glob server. So now this is the final result when I successfully bring from every hosts. Now let's fill in the table in the slide. So as you can see, the actual result matches our expectation. All hosts successfully communicated with the server. Now we'll move on to the live demo where I will explain the encapsulation and decapsulation process using the OSI model in the Packet Tracer. Now we try to open log server web browser in Xio BC5. And before sending the HTTP request, the client first needs to establish a TCP connection using three-way handshake for reliable connection. Now the client begins the process of encapsulation from layer 7 down to layer 1 at layer 7. This way an HTTP GET request at layer 4, a TCP header is added. The source port is 1041 and destination port is 80. At layer 3, an IP header is added with the source and destination IP, and at layer 2, it adds an Ethernet header with MAC addresses for local delivery, and finally at layer 1, it will deliver over the bits to the medium cable. So when the request reaches the server, the decapsulation will happen. From layer 1 to layer 7, data will be received at layer 1, and then the server will check for matching MAC address at layer 2. At layer 3, we check for its old IP address. And in layer 4, the server will read the TCP header to see the port 80, which means HTTP request. And at layer 7, the server will read the actual message and get ready to respond. And then at our layer, it will encapsulate again and send back the response. And after the data exchange, both sides use a FinOps process to close the connection. So for saving time, we will switch back to real time and then open the package, the BC file. And here it is the website. And this is also the end of the task for demonstration.
In conclusion, we successfully completed task 1 by setting up our network topology and addressing. We then implemented task 2 with the VLAN creation and task 3 for seamless inter-VLAN routing. Finally, we achieved full network connectivity across all segments as per task 4. Thanks for listening.